So good morning everyone. It is my pleasure to welcome here Łukasz Tomków, who came to give us a talk about the project called ITER and its current status. So,
okay. Thank you. Thank you very much for the invitation. It's particularly nice for me to present at Salesian University. I'm Salesian as well, coming from Wrocław. So I'm going to present you current status of ITER project. Here you can see a beautiful bird's eye view of the site. It's actually quite huge. From here to here, it's more than 1 kilometer. For example, this building has 200 meters in length. So this is one of the, if not the largest scale project currently under construction in terms of scientific projects and also in terms of its price. Okay, so let's move to it. What is the goal of ITER? It's to achieve fusion on Earth. So the idea is to have energy positive balance of the fusion reaction. It has been claimed to be achieved recently by National Ignition Facility in the US. However, it was some, I would say, clever accounting here. And at least in my personal opinion, at the moment, we don't have practical technical possibility of using that technology for efficient energy production. On the other hand, magnetic confinement fusion appears to be more relevant for that, mostly because if we obtain proper degree of control over plasma, we should be able to sustain a long-term fusion reaction, which then would allow us to actually drive energy-producing generators. All right, so in ITER, we plan to perform a deuterium-tritium reaction in which we obtain atom of helium and also a high-energy neutron. Basically, the idea is to obtain conditions which are known as ignition and also burning plasma. That means that the plasma can sustain its own fusion only based on energy which is maintained within plasma volume by helium particles, because since they are charged, they can be controlled by magnetic fields. So basically their energy is able to remain within a confinement zone, and energy which is carried by neutrons can be captured by an element which is called blanket wall. There it is deposited as heat, and this heat is removed as, basically as thermal energy by water, which then, as in any other power-producing plant, can be turned into steam and then run turbine and the generator. However, this is not what is going to be happening in ITER. The main goal here is to understand the physics of burning plasmas and to actually achieve, for the first time, positive energy balance. Now, to run this reaction, it is required to have very strong and very precisely controlled magnetic fields. How it is going to be achieved, I will show in a second. And also to obtain extreme conditions of plasma. So it's mostly temperature, but also high pressure, which is being maintained by these extremely strong magnetic fields. All right, so how does it work? In very simplest terms, we inject, the idea is to inject a mixture of deuterium and tritium, then to inject electric current to heat it up, and use other heating methods. So in ITER there are 3 of them. So this is, injection of electric current is, not exactly, because basically it's the current which is induced in the torus of plasma by this huge magnet, which is central solenoid. The other method is injection of high energy neutral beam. So this is done using accelerator, which from the beam of which is then neutralized by electrons. So basically we accelerate ions, then neutralize the beam with electrons, and then with this neutral beam we are able to penetrate into the plasma. And the third way is to use high energy radio frequency electromagnetic waves. So using those 3 techniques, it is possible to obtain the required 150 million degrees Celsius, Kelvins, it doesn't matter at this scale. And at this point, we should be able to obtain fusion with high enough energy to overcome Coulomb forces. All right, so there are many technical challenges connected with the construction of ITER. It consists of, it is estimated, roughly 1 million parts. However, the real number is actually much larger because some of them are in the assemblies. Actually, I am personally responsible for, I think, 400,000, so I'm quite convinced that other people have similar number as well under their jurisdiction, let's say. I will just show the largest elements. Vacuum vessel is the most internal part of the tokamak. So this is well, the element which actually holds plasma. So this is how it's symbolically shown. The goal here is to obtain a very clean environment in which there are no impurities. Presence of any impurities may cause plasma to shine, and this shining means basically loss of energy from the point of view of the tokamak, because instead of using energy to propagate the reaction, we have some losses in form of electromagnetic radiation. So the goal here is to have as pure vacuum environment as possible. So we have very stringent requirements towards any materials we put into the vacuum vessel. Each of the elements which are being put there is vacuum tested, and we take very particular care not to introduce any impurities. Now, there are also other issues about which I will talk in the moment, connected with corrosion and other problems which may be caused by those impurities. Now, this is going to be one of the largest vacuum chambers in the world. I think it is exceeded only by the one which is in NASA, where they test satellites and other space equipment. It also serves as a containment barrier. So we are going to inject the tritium, which, as you certainly know, is highly radioactive. And the goal here is to also prevent propagation of tritium to the outside world. There is a number of methods in which the radiation is being stopped. So this is primary containment, then we have bioshield, and several other methods, including the building itself. All right, another important aspect of the vacuum vessel is the fact that its walls are covered by the blanket modules. This is what I mentioned, the part in which heat from neutrons is being captured. In ITER, these blankets are going to be cooled by water, which means that we are already going to receive some useful heat. Another goal of the blanket is to breed tritium. So that's one of the ideas how to sustain fusion without injecting tritium, which actually, when ITER operation will start, will probably be very quickly depleted. The problem is that global reserves of tritium are very small. It mostly, I mean, currently it comes mostly from the commissioning of nuclear weapons. So it is quite scarce resource. So in order to actually run fusion power plants, if we ever have them, we also need a way to provide fuel, and one of them is to actually produce the fuel in the reactor itself. So this will be the goal of breeding blankets. Right now it is all, at the moment, a bit theoretical. So one of the goals of ITER is also to check that. There is idea of checking different types of breeding blankets to see which one operates best and to understand better this process. All right, another part of the vacuum vessel, well, actually it's the part which is installed in vacuum vessel, is a divertor. I don't think it's shown in this picture. Divertor is the part in which the product of fusion, so let's say sort of ash from this reaction, which is helium, is being removed. This is the part which has the highest thermal loads. They have been compared with the loads, with the thermal loads on space shuttles when re-entering the atmosphere. So in terms of engineering, this seems to be the most challenging part. So basically to produce elements which can survive this sort of conditions, this sort of thermal loads for a prolonged period of time. So it is expected that pulses in ITER will last up to 15 minutes. so to have elements which are able to survive that is quite challenging. Now, one of the parts for which I am responsible are the cables which reach very close to the divertor. They have to be covered in very high purity copper in order to obtain proper reflectivity, just to attempt to deflect part of the heat. So it is hugely dangerous here, especially that cables themselves are also vacuum tight, and any hole will prevent their proper operation. All right, second important part is magnetic cage. So here you can see a schematic of this system of magnets in ITER. It consists of three main types of magnets. So this is central solenoid, which I mentioned. This is the part which is used to generate solenoidal magnetic field. In this element, we are going to have ramped magnetic field, which will induce current in plasma. So current in plasma, which will be going here inside, is expected to reach 15 megaamperes, and the rough value of magnetic field is going to be 5.3, I think, 5.4 Teslas. That means that we are going to be dealing with huge forces. It was already observed in other tokamaks. The largest tokamak in work currently is, well, I think it's being decommissioned now, but it's JED, and there are stories about interactions between plasma and magnetic field so strong that they were able to lift up the structure of the tokamak, which weighs many tons. So basically, the forces are huge, so this is another challenge. All right, so except for central solenoid, we have toroidal field coils. So these are D-shaped coils. They produce toroidal magnetic fields, which is a primary method of containing plasma. And the last one are the poloidal field coils here. They are shaped like, well, basically they have circular shape. And they are one of the largest and strongest magnets ever produced. The production of them was actually, well, really logistics of the production was so challenging that they are one of the few big parts which have been produced on site. Most of the elements of ITER are being produced off-site by member states, well, in the economies of member states. So these smaller coils have been produced outside, but the biggest ones were expected to not be able to be transported in any proper way. So they have been produced on site. Okay, this entire magnetic system produces complex magnetic field, which is designed to contain plasma. There is a number of smaller coils which are used to fine-tune magnetic field in different locations to prevent any events which may disturb the plasma and cause instabilities that may lead to damages to the tokamak. So basically, in order to avoid that, very fast control systems are required, which need to react extremely quickly. Now, it is very much expected that some instabilities will occur. It's quite certain that they will. So that's why there also exists a disruption mitigation system. This disruption mitigation system is using pellets of solid argon or other noble gases, which are injected into plasma to quickly cool it down and to prevent any damage to the tokamak. So it's actually quite interesting because basically we use argon snow to stop the reaction. Here you can also see the figure of human to have the size comparison. Okay, let's move further. All of these elements which I showed you are confined inside the cryostat. So cryostat is basically the element which keeps superconducting magnets that I showed before at low enough temperature. They are cooled by liquid helium to 4.5 K. So there is no, as far as I know, superfluid helium used there. And this element is designed to provide a cold environment. Now these holes that you can see here are called ports. These are access points into the vacuum vessel in which we put diagnostic equipment. Here are the vacuum pumps which remove helium from the reaction. And here are, for example, inserts for neutral beams. So basically they are all used to interact, to measure plasma environment within the tokamak. This element, if you can imagine size, so here is a person. It has 30 meters height, 30 meters in diameter. So this height is comparable with 10 stories building. So as you can imagine, one of those big blocks outside in Opava is roughly the size of this element. So it consists of 4 parts. I will show you in a moment. Some of them are already inserted in the tokamak building. So there is a bottom part, middle part, I think it's in 2 halves, and the top part, the lid, which currently sits outside of one of the buildings. So it's truly a marvelous sight to see. Okay, ITER is huge collaboration. It's actually one of the only global collaborations on this scale in between so different partners. So you can see that we have European Union, so us, Korea, also Russia, Japan, United States, India, and China. So this is actually quite fascinating, this collaboration, that many partners with very different geopolitical views and geopolitical interests came together to create this technology. So basically the idea here is that this technology will help entire world, so entire world should work together to obtain fusion, to solve many of our problems. Actually, entire collaboration has been started during the Cold War. It was one of the first scientific projects between United States and Soviet Union at the time. However, after the fall of Soviet Union, much of work has been taken by European Union. Actually, I think in financial terms, France is the largest contributor because it's, of course, located in France. Then the rest of European Union through Euratom, and after that, each of the partners. So as far as I remember, European Union has more than half financial input into the project, and the remaining partners have their equal shares, except for that. Okay. Of course, there is some Czech contribution, so majority of that is done in terms of research, and there is a lot of testing being performed in Rzesz, Rzesz, I hope that Rzesz. Okay, I hope that I try to pronounce it well. So there is a lot of research ongoing on breeding blankets that I mentioned. So it's particularly important from the point of view of any future fusion reactors. And also they perform some tests of rad-tolerant and also rad-hard electronics. The environment outside of the tokamak is extremely demanding in terms of radiation loads. So there are huge fluxes of neutrons, which very negatively affects any electronics which is put in them. So in order to ensure proper operation, all the electronics needs to be resistant to this radiation. So this is one of the inputs. The second one is also scientific. Right now in Prague, there is ongoing upgrade of compass tokamak to produce compass upgrade tokamak. As you can see, it is fairly similar in geometry to ITER. However, it is much smaller, so as you can see by a figure of the person. But it is extremely important because since this geometry is so similar, all the analysis of plasma physics will be very relevant for the behavior of plasma in ITER. So the idea is to have very high magnetic field in which all the plasma containment modes can be tested. And also this tokamak is going to have the divertor in which the type of heat loads is also going to be analyzed. So basically this tokamak is the upgrade of this one. And then there is also smaller tokamak Golem, also located in Prague. That actually makes it one of few towns in which there are 2 tokamaks. Both of them are used for this smaller scale research, but they are a very important part of a big network of tokamaks supporting ITER projects. There are many others, like for example West, which is actually next door in CA, close to ITER. Then there is also Keisar in Korea, J60 in Japan, East in China. and many others. So basically, most of the tokamaks in the world currently support ITER in terms of the research output. All right, so this is how the site looks like more or less currently. So this is the photo from March. And there is constantly ongoing construction works. For example, here right now, a new building is almost completed. So only after 2 months since this picture has been done, a lot of progress is already visible. So I actually, every time when I am at work, I walk through here and I can see every week there is some new wall ready. It's actually quite fascinating to see this progress. The most important building, of course, is the tokamak building. So here in this part, there is a pit in which the tokamak is being assembled. And this is assembly building in which currently existing sectors, I will show the sectors in a moment, are being kept. Now, despite being connected, these are two separate buildings. The tokamak building is heavily secured against any risks of earthquakes and other possible problems. So the idea is to protect tokamak as well as possible. Other important buildings include the colloidal field coils winding facility. So this is a huge building in which the production of coils, of these colloidal coils that I've shown, has been performed. And the switchyard is basically the power supply for the tokamak. So it's standard industrial switchyard. Other important elements are magnet conversion buildings in which all the conversion of power supplies to the magnets is going to be performed. Cryogenics plant, which will provide cooling for superconducting magnets. And here we have radio frequency building, which will provide one of the heating methods. Here under construction is neutral beam building, which will house the accelerator generating the neutral beam. Tritium building is also under construction. However, it won't be needed at the moment, mostly because tritium operation is planned for further in the future. So it is still under construction, among other buildings. So here, actually, it is almost finished, is the control building. Headquarters exists almost from the very beginning of the existence of ITER. All right, the rest of the buildings is in more supporting role. There are some warehouses. Cryostat workshop has been used to assemble parts of cryostat which came from India. Here you can actually see one of the cryostat elements being outside of the building. So it's not yet, this particular part is not yet put in the pit. What else is interesting? I mean, it's actually quite nice to see at the scale of this element. How huge is that compared to this building, which, as I mentioned, has 200 meters length. So it's really big items. So let's look at some photos from the actual assembly. This is the bottom part of the tokamak being transported through the assembly building. So this is this building. So it is transported from cryostat workshop through this building to the tokamak pit. Again, you can appreciate the scale of entire endeavor. These are one of the largest cranes in Europe. They are able to carry combined 700 tons in total. And this is, I think, the second heaviest element which is being put in the pit. The heaviest is the second part of the cryostat. This is how it looks like when it's put into the pit. I've visited this place once. It's truly marvelous look right now. So indeed, here you can see the inlets from the building into the ports. So this will be access points to the tokamak. It is all very nicely symmetric at the moment. However, soon it will start to be filled with equipment. So this is a lower cylinder of the cryostat. This is the heaviest part, which is already put into the pit and which will be the part of the tokamak. So again, here we can see these port entrances, which I shown on the diagram. So as you can see, it is actually being realized and it already exists. So this was one of the hardest pieces to be assembled. It needs to be assembled with huge precision, and fortunately most of that was successful. All right, so so far we have, as you can see in the pit, two parts of the cryostat. This is the photo of cryostat thermal shield being installed. Thermal shield is used to prevent thermal radiation from entering, well, from interacting with superconducting magnets. All right, we'll actually go back to this topic soon. This is the installation of the first poloidal coil. This is the smallest one among 6 which will be installed. So here you can see people. This is, compared to everything around, a relatively small element, but no less important. Also here you can see the first module of central solenoid. So this is huge pack of superconducting coils, which, as I mentioned, will produce current in plasma. All right, so this is well, poloidal coil number 5, which is second poloidal coil to be installed. Again, you can see here growing solenoid. This is the picture from September 2021. Well, COVID didn't stop works. It made them very hard, but it was, I mean, the operation was still progressing. So it was particularly challenging because there was very limited number of people that could enter the site. However, as you can see, the work still has been progressing. All right, this is one of the most impressive views that are available now at ITER. This is the first sector of the vacuum vessel. Now it's just, I mean, on this photo we can see just the vacuum barrier, so it's only the steel part. Soon, I mean, we'll also see the photos of it connected with the magnets, but you can already appreciate the scale of it, how huge and impressive it is. These yellow parts are the elements are the connectors to which the blanket modules will be installed in further future. And here is where the divertor will go. So basically this entire volume here will be the torus of plasma where the fusion reaction is expected to be occurring. All right, so this is just the part of the entire sector assembly. So here is the toroidal coil. So this is one of 18 huge superconducting magnets. Two of those magnets go into each sector. So we will see the entire assembly in a moment, I hope. So this is thermal shield. We'll go back to this topic also soon. And I hope, yes. So this is the entire sector completed. So you can see 2 coils installed on the sector. And the blanket modules are not there yet. And the divertors will also be installed later. Installation of the divertors and the general installation of items inside the sectors is a separate, extremely fascinating topic. It will be done mostly by robotic arms and automatic remote handling system. So it is going to be one of the largest ones in the world. It is, I mean, well, it all needs to be done, at least be able to be done automatically, because after operation of the tokamak, all of the structure will be heavily radiated, preventing any human access. And, well, obviously to avoid irradiation of people, it all needs to be done automatically, especially after the start of fusion operation. However, we already need to have the technology for that, which is being developed. Now, the issue is that even in future tokamaks, so it's not only the issue with the test tokamak, every now and then the exchange of blanket modules will be required. So right now the development of this remote handling technology is a must. All right, so this is one of the huge successes, but also it showcases some challenges about which I will say in a moment. So the first sector has been installed in the pit in May 2022. Now, when all of them will be installed, they will form complete torus, and the operation of the tokamak can be started. But we'll go back to this topic soon. All right, regarding the status of other systems, most of the supporting systems are in advanced phase of preparation. So for example, here we can see the power supply systems, which are mostly installed. Same goes for heat rejection system. So these are cooling towers which will be used to remove heat generated by the tokamak and also injected there. In the background you can see a nice view of Southern Alps. However, the system of the actual cooling system of the tokamak is not yet ready, well, for obvious reasons, because there is nothing yet to connect it to. However, each of the sectors will be cooled by water, and well, also cooling must be provided to any other associated system. So for example, we will have gyrotrons which are supposed to deliver 50 megawatts of energy into plasma, but that will require at least 100 megawatts to be delivered to gyrotrons. So these 50 megawatts need to be removed from that. And that goes for any other heating system, for any other accompanying system. So that's why we have 1.2 gigawatts of heat capacity to be removed. I mean, in reality, it will be probably less. However, depending on the way how ITER will perform. So for example, how high power will be achieved. Right now, ITER is designed for 500 megawatts, but it's quite possible that at some point in the future, it will be refurbished to go even further. So heat rejection system will be ready for that. All right, so cryogenic plant, it is mostly installed. Right now there are tests of nitrogen installation being performed. So at some point in near future, helium system will be run, hopefully working properly. Okay, most of the cryo lines are already installed. So by the way, you can see here also the scale of that. Compared to any other cryo lines, these are one of the largest in the world. It is said that ITER cryogenic system is the largest in the world, which is not strictly speaking true. It is the largest concentrated system in the world, because the title of the largest overall in terms of power belongs to still to CERN's LHC system. All right, well, installation of power conversion systems for magnets is almost complete again. So all this supporting system, I mean, the work on supporting system is going very well, mostly because it's in most cases industrial standard. There is no particular need to develop new technologies for that because we already have it. Now it's another interesting thing for ITER project that the attempt is to build it with existing technologies. However, given the scale of the project and the fact that it's first of a kind, some new ideas still need to be developed. All right. So the electron cyclotron resonance heating system is also almost finished. So again, it's not particularly interesting to look at, mostly because this is again industrial standard on a huge scale, but still most of the components are standard. All right, neutral beam building is being constructed. So actually, I was there just on Tuesday, and this wall here already stands. So it is going quite well. Soon it should be finished, and I believe that installation of the accelerator will also be started soon. Control building, well, the construction of the control building is also finished, and soon it will be started to be filled with control infrastructure. So this is where actually the entirety of the tokamak will be controlled from. So it's very close. So here is, let's say, the tokamak building. All right, there is a number of significant challenges, as always, in the project of this size. Some of them technical, some of them logistical, and some of them coming from outside. So, for example, the COVID pandemic caused some delays with the execution of contracts and other agreements. And there are also some issues with the first sector installed, about which I will mention in a moment. Also, interaction with French nuclear regulator is quite interesting, mostly because they also learn in parallel to us. We need, of course, to obey French nuclear law, French regulations, which can be quite convoluted and complex. And the problem is they are mostly designed for fission reactors. Now, one of the examples is the issue which, well, maybe it didn't stop construction, but it was feared that it will, was the discussion about the accuracy of neutronic simulations in the tokamak. So normally the regulator is sort of accustomed to 2D codes, and in the case of ITER, a 3D code is required, so there needs to be a lot of work to prove that the computational code which is used for neutronic simulations is well validated. So this is the sort of things that the project needs to deal with. And well, another problem is that given all the possible delays and some changes, many important decisions need to be taken. So, for example, right now there is interesting discussion about the composition of the first wall. So whether to use beryllium or tungsten for that. And it's particularly important because any decision which will be taken at this point of the project will affect all the tokamaks in the future. So basically, this is sort of defining moment for entire technology and for entire future of fusion power plants at the moment. So it's quite a responsible decision to be made. Fortunately, it's not mine. All right, so technical challenges. As you have seen, this first sector which was installed seemed like a huge success. However, it revealed also some problems. So some leakage has been detected caused by chlorine corrosion. This leakage was detected in the thermal shield, and it will need to be repaired. So quite possibly this entire sector will have to be taken out for repairs. There is a plan for repairs. They soon should be started. So basically we need to find for an accelerated process contractor willing to repair it and able to. Another problem is some non-conformities, so basically misshape of the vacuum vessel. It also affects my project a bit because I had to modify some placement of my components, and it also will be repaired. So basically, since the project is of such a huge scale and since it is again first of kind, these problems are expected to occur, but unfortunately they will also cause probably certain delays. All right. Now the last thing, since I'm talking at physics faculty, maybe a bit of explanation. So basically at the moment ITER project is mostly an engineering project. There is not much science happening at the moment there because we are basically building scientific equipment. But there is still some interesting, let's say, semi-scientific things that can be done. So this is my personal responsibility. It's calorimetric system of the tokamak. So the job of this system is to calculate the thermal balance of the machine based on parameters of cooling water. So for that, I analyze all the thermal flows in order to create sort of balance to find the fusion power. So I cooperate very closely with people from heat rejection system. So these are those cooling towers that you have seen. I get some sensors data from them to check how much heat is being removed from the tokamak. And then by some sort of heat accounting, I am trying to find all other thermal inputs and outputs other than fusion power. By summing all of that up, I am supposed to get the fusion power. Now, since the structure is so large, it has huge thermal inertia, which makes that measurement not particularly relevant for control. However, it is of particular importance in cooperation with a neutron sensor. So it is quite well-known problem in fission power plants that these sensors tend to have certain drift. So basically, the accuracy of neutronic sensor measurements decreases with time, and they need to be calibrated sometimes. And in fission power plants, it is done with exactly the same system. So basically, you have completely independent system which gives us the value of power output of the reactor. And by comparing this power output with the output of neutronic sensors, by integrating them over the pulse, we should be able to check for the drift of neutronic sensors. So right now I'm working on creation of the simulation algorithm for that system. So here you can see what the actual power is. Now I implemented here, these are not real data. I just assumed that there will be 20% variation in power output from the tokamak. And due to thermal inertia, it translates into this sort of softened value of the red power, of the measured power. By using some mathematical tricks, it should be possible to obtain more time-dependent reading. So basically, by taking the derivative, which will indicate, well, should indicate that the average temperature of the tokamak, we should be able to understand the speed of change, which is basically the power. So this is hopefully what will be possible to obtain with the system. So rather close approach between the reconstructed and actual power. Right now it is in a very early stage of development, so it's sort of pre-conceptual design, just to check if it makes sense. In my opinion, it does, mostly because it is very well proved that it already works with standard fission power plants. Okay, so in order to be able to prove that, I had to run some sort of study on accuracy of the system. So I created some simulated data to check what is minimum and maximum reading of the system, yielding the accuracy of plus minus 6% in nominal operation range of the tokamak. Now neutrons are expected to give 10%, so it's already an improvement. With the further development of reconstruction algorithms, we should be able to go to even better accuracies. Now this is quite relevant for the operation of the tokamak, because the regulator gives us the license only to operate up to 500 megawatts. So so they expect us to operate, for example, in this case, in the range of the accuracy of the neutron system. So that means that if we have the license to work at 500 megawatts range, if the accuracy of neutron system is 10%, we are supposed to operate at 450 megawatts just to be sure that we never exceed 500 megawatts. So if we will be able to improve it to 6%, for example, we can go further 20 megawatts. So it's already, let's say, billions of dollars in the future operation of the power plants. So it's very important from that point of view. But as I said, this is still a pre-conceptual phase. I hope that in some years I will be able to come back with better and actual results. Okay, so that concludes my presentation, and thank you very much.